We're live and ready for action. So we ended off last time with this wonderful set of colorful curves, talking about things that are completely not useful to your grades, but we will continue talking for another 10 minutes about. But before wasting 10 minutes on this, I guess as one does, I kind of maybe missed some little details of things from last time that might be useful to mention. So let's just fill in a couple more, points that are probably useful for you to know for various reasons. One of them being that you'll probably be graded on questions related to this, so why not mention it? And so, yeah, let's spend about 5 minutes just kind of pointing out a couple more things about this regularization business. Okay. So in particular, let's remind ourselves a little bit of what happened. So there was this observation that functions that have, these weights, like in particular, if you think about polynomials, and if you look at their weights, their parameters, their coefficients in front of the polynomials, and you kind of plot a bunch of them, you'll notice that they look real curvy when the coefficients are large or when the weights are large. And so the idea was complexity is related to the size of these coefficients, these weights. And so if we make the coefficients small, then maybe our function's not so complex. And if we make them large or allow them to be large, then we allow complex functions. And the way we kind of, and this is exactly related to this whole thing where we're trying to control the complexity of the functions or the function class that our learner is going to use to minimize some sort of loss. Okay. And so the natural way to do this was to change your function class such that you kind of limit the sum of these coefficients, their absolute or squared values. But we talked about how kind of the nicer way to do this for optimization reasons is to actually just move this into the objective and to change the usual empirical risk to what is now called a regularized version, or the empirical regularized risk. And all that happened is we added an extra kind of penalty to our loss, which penalizes large weights. And the larger the lambda, the more you penalize them. Okay. And the way to interpret this is that now our learner will be minimizing the following function, and it will output, the learner will output a function. So maybe I should write this all down. There's a learner. It takes in data. It outputs a function. We call this f hat. I'll call it f hat of lambda now. And f hat of lambda is going to be equal to we define it for any particular feature x in the usual way. Okay, here we use the polynomial thing. So maybe even more generally, right? We had this learner which depended on the polynomial function we use as well. So maybe I should call f hat depending on p and lambda. We kind of had this before. And so now this function here will be, it uses the p for the corresponding feature map, the phi function. This we know, this just changes our features to be higher dimensional, in some sense to have more interesting behaviors. And then this w vector used to be called w hat, and maybe we'll still call it w hat, but now it'll depend on the lambda we kind of choose, in the sense that this will be the definition of this w hat lambda now. Okay, so now if you set lambda to 0, you get 0 times this, so then you just end up minimizing the usual empirical risk. For any value of lambda that's non-zero, you are minimizing a different function. Turns out it's still convex. And yeah, that would cause for a different learner. And I probably should also subscript this with lambda here. And so this is important to note, that our learner now changes in the sense that if you change p and if you change lambda, you get a different learner. And what is different between the learner is that if you change p, it's using a different function class, as we talked about, because it's searching over these kind of p-degree polynomials, and if you change lambda, it's minimizing a different objective. So it's minimizing this empirical regularized risk. Okay. And yeah, we talked about how to minimize that. That was just some optimization stuff. But I just wanted to talk about this plot one more time here, which is in this plot, it should be interpreted as when you, like this lambda here on the x-axis, it's changing the corresponding like function that the learner is minimizing. It's changing the empirical regularized risk because lambda is changing. And so each one of these points is the model. We're trying to look at the empirical risk, or sorry, the expected risk of the corresponding function or predictor or model that a learner outputs for different values of lambda. So each one of these points is a different model, and it's output by a different learner. The learners differ by the lambdas they use. Okay, and this idea of like sweeping over this lambda value is like this idea of sweeping over a hyperparameter. And you really should think about it as you're training a different learner on the same, like like when you actually implement this, you're using the same training data set. You train different learners. They differ because they use different lambdas. Each of them produce different models potentially. And then you want to evaluate how are those models doing that each one of them produce. So you would then get an estimate of these points on a test set. And then you're like, okay, seems that this learner, when it used this lambda over here, outputs kind of the best model. Okay, so that should be clear. And in your assignments, you have this kind of like outer loop, or I think so, and you train, well, maybe that you don't really implement the outer loop, but the plots do, and they will literally train your learner for different values of lambda. Okay, great. And there's the other thing I wanted to talk about is the effect of lambda on the variance, the bias, and the approximation and estimation error, and on this expected predictor versus the F-star predictor. So let's just have that last discussion, which will go, I guess, down here. So here's the question. So if lambda increases, what happens to these various things? Yeah, let's do this first. Well, let's just do it from what we already know. So lambda increasing means you penalize large weights more. And large weights being penalized more, so you can think of it another way, large lambda probably means your weights are going to be set smaller. Smaller weights mean less complex function. And what was the story about less complex functions? Well, less complex function means, well, maybe you can't exactly match kind of like F-Bayes, or you might not be able to represent the data the way you'd want. So the bias is going to go up, right? But since it's less complex, it can't vary as much. So then the variance goes down. Okay. But notice that, okay, so these are bias variance. But notice that lambda is something that affects your mu-like objective. It affects this empirical regularized risk that we're minimizing. This guy over here. And that has nothing to do with the approximation error. If you remember what the approximation error was, that was the error between the function that minimizes the true risk from your function class relative to F-Bayes minimizing that. So the point is that the approximation error really doesn't get affected. That's just a property of your function class, and your function class technically hasn't changed. It was like a fixed polynomial. So we'll say that the approximation error is unchanged, or is the same. And the effect on the estimation error will actually kind of capture both of these. And so this is why like bias and variance is somehow more useful to discuss when you're using regularization. And the estimation error is complicated, so we won't talk about it. Because it's really going to be a function of how are these both kind of changing. Okay. And another thing to observe is that if lambda is not equal to 0, then F bar, which is the expected predictor, is not equal to f star in general. Oh, that's not how you write not equals. This is not equals. Okay, not equal. And let's talk about why. We can do it through the visual plot. And yeah, here's good. So this was the case where, let's say lambda is equal to 0 for now. Well, we had that like f star and f bar were this green looking function. We chose a really complicated polynomial. We don't penalize the weights at all. And so, yeah, so this would be like your average predictor. It's kind of the average over this orange and this purple and some like on and on of these different lines you would get for different data sets. Now suppose we set lambda really large. So we really don't want these weights to be large. You can think of that as like basically forcing it to be something like a line. It really can't vary very much. Yeah. And so what's going to happen is you're going to get a bunch of lines here. However, f star doesn't get affected, right? Because f star has nothing to do with how you changed your lambda. F star, if we can find its definition long ago, is over here. It's just a minimizer of the empirical risk over the function class you chose, nothing to do with lambdas. And so f star will stay the same. And so if we go back to this type of plot here, your f star will still be this green line. However, if we make the lambda really, really large, then f bar will become something like this corresponding green line here. And so you can see they're not going to be the same in general. Okay. And hopefully you can also see that here, this would be like kind of really low lambda. This is like lambda equal to 0 kind of case here. And there's a lot of variance between these predictors. Lambda being large, you can see there's a lot less variance between like the purple, the orange, and the dark green lines. Okay, so maybe that was the last kind of missing thing from last lecture that was not appropriately covered, and you should know. Okay, so that's going to be the end of this section. And before moving on to sort of a different way of defining your learner, that's not this minimizing the empirical risk, we review this double descent thing for fun. Okay. And so just to remind you, this what is this double descent business? The double part, or what's descending? Well, remember this like plot we saw where you're increasing the polynomial degree and you descend. This is the first descent. And then you go up, and then I told you that was kind of the end of the story. Well, it so happens that sometimes you can go and descend again, and it can go even lower. And that's the second descent. Okay, so how does that happen? And I drew some plots, and I'm going to erase them because you probably don't remember what happened, and it's really easy to redraw them, so we'll do it again. So you start with this polynomial degree of 1, and you find like a best fit. It might be like a line, maybe that's not so good. Then you fit like a polynomial or a squared function maybe. And that's like maybe a bit better, but not perfect in terms of the empirical risk. And then you go on to fit this cubic one. And what I was saying is that it turns out if you have n data points, so here it's 4, you can fit those data points perfectly, assuming that for every x value, there's only one y label, which of course is not very realistic, but in this case, it's true. Well, then you can find a perfect fit with a cubic polynomial. And maybe it'll look something like this. And there's exactly one cubic polynomial that'll fit it. And so around here, you can see that fitting new data point, like the data is probably something like this, let's say, maybe. So at these points, it's fitting it quite poorly. Maybe at this point, it's fitting quite poorly. Okay, so that's one observation. And then you can go up to higher degree polynomials. And when you go up to a higher degree, even 4 or 5, well, even if you go to 4, there turns out to be like an infinite number of functions that can fit this data well. And some of them are really bad for predicting new data. So an example might be like this. Like maybe this is a 10th degree polynomial. It chooses to fit it like this. That's kind of terrible. But there also exists one that doesn't look this ridiculous. And it might look something like this, maybe. Okay. And so the question is, if you go up to these higher degree polynomials where the degree is kind of larger than your number of data points, so a lot of choices to make. even for a specific data set. And maybe one more precise way to write this is, so far we've been talking about this, right? We were like, oh, my f hat is going to equal, okay, equal to the argmin function in my function class of L hat of f. And no one has kind of pointed out that there might be something going on with this equals, like this is technically wrong. What do I mean by that? Let's just take another step back before we get to this. This argmin notation, the first way I introduced it, or before the argmin thing, there was this like min thing, you min of a set. And if you write a set, let's imagine this is your set. Okay, well, let's write it as a tuple so we can have duplicates. If you write the min of like 1, 2, 1, okay, the minimizer is clearly 1. But there can be multiple, let's call the argmin the index, okay, at which this happens. Well, you can see there's like at index 1 this happens, and at index 2, or at index 3 this happens. The point is, in general, there can be multiple f's that minimize this, right? There can be multiple f's that achieve the exact same value. And so in general, an argmin is actually written as a set. It's the set of all functions that achieve this minimization. So technically, we should always have been writing this, that f hat is any one of the functions that minimize this. Okay. And so then the question becomes, when we run gradient descent, we're clearly not outputting a set of functions. We output one function. And it's minimizing this. So it chooses one from this set, right? And I just said if the polynomial degree is really large, compared to the number of data points, there's a lot of functions to pick from, right? Remember, this is a fixed data set stuff. So the question is, what does it pick? And what you'd like is it for to pick kind of the least complex one that fits the data points, right? This is like kind of what you'd want. In other words, maybe you wanted to pick the one that has the like a small, sum of weights, sum of parameters. And you can think of regularization as a way to enforcing it to specifically pick that one. If there is another way, like if there's a set of choices, then when we add regularization, we're really saying out of the set of choices, I want the one that has the smallest kind of parameter, like sum of parameters squared or whatever. So that's what we've been doing with regularization, actually. But it turns out that under kind of like certain conditions, without even adding regularization, gradient descent already does this on its own. Okay? And so does the closed form solution. It actually ends up picking the function out of all these functions that fit this data perfectly for higher degree polynomials that ends up having the smallest sum of squared parameters. Okay. And so for that reason, if you actually end up plotting this thing we've been plotting before, and you run gradient descent under like a good choice of step size, and you run it for long enough, and you initialize kind of correctly, or if you just get the closed form solutions, you can actually find behavior like this, which is like, let's say polynomial degree 1 is here, and then maybe 4 is here, and then you get to like 7, 10, and then you really start pushing it. I don't know. And imagine n is like 4 or something. Well, then it's very possible you might observe a plot like this. So so far we've been seeing something like this. Yeah. And we were like, let's pick this point. Well, if you keep running it, there's a point where actually, maybe I should pick n to be, this is in theory what should happen. So if you pick n equal to, let's say, 8, well then with a 7th degree polynomial, you will fit it perfectly. So at this point, you can fit the data points perfectly, but you're probably gonna have a large error on the test set. Or in other words, this was the expected risk on new data of f hat. And then after this comes the point at which there's many polynomials to pick from. And so because of this kind of choice of gradient descent or the closed form solution of picking the minimum squared sum of parameter choice, it might start curving the other way and actually just keep going down. Maybe not to 0, but something like this. And it can actually, like, I'm really exaggerating, but it could actually be much, much lower than the other case. And this was like an observation made not that long, I mean, like less than 10 years ago, called this double descent thing. And it's kind of interesting. So in some way, people call that like gradient descent has implicit regularization built in. But of course, in practice, this comes with lots of caveats. And so people still use regularization. But this was kind of interesting to know. Okay, that's all for that. And okay, maybe one last thing, just like the thing to note is at the polynomial degree 7, where you can perfectly fit things, since there's exactly one function that like fits it perfectly, that function is really like rigid or restricted. And so, yeah, that's why it's like kind of a lot worse than when you go to higher polynomials. Okay, that's the end of the story. Let's move on. So we are supposed to talk about maximum likelihood, if I can find where the file is. There it is. Okay, blank sheet. So maximum likelihood estimation, that probably makes no sense. And it's going to hopefully make some sense. And it's just going to be a strategy to do something that we're going to need for a different kind of learner. And so forget about maximum likelihood for a second, but I will write that this is kind of the topic. And I will hopefully motivate why we care about using such a strategy right now. And this is something you will learn in statistics if you take a course on that. And you'll learn it in the context of if you have some like distribution and you would like to estimate the distribution from data, roughly speaking, this is one way to choose to estimate it, to pick the distribution based on data. Okay, but why do we care about this at all? And we're going to care about this at all because we're going to try to design a different learner, okay? And so to design a different learner, let us remind ourselves what is our goal, right? Our goal is to, we've said it many times, it's to, predict new data well. So we want to minimize the risk, right? This L was the risk. This is kind of a numeric, like a single number that represents how well we do on new data. This is L of F. If you remember, this thing is equal to the expected value of our loss of our function or predictor on new data X compared to a new label Y. And that's the weighted average over all X and Y you expect to see based on the way the data is being gathered. And obviously, we want to minimize this thing. And that was what this like F-Bayes business was. And we wanted to pick the argmin function really from this function class. And that's like the ideal scenario. That was F-Bayes. Okay. And we said, okay, we can't quite do this. Even forgetting about the function class business, we don't know what this is. And so we had to estimate, well, we had to do something, right? We didn't know what this was. And why didn't we know what this was? Well, because if we write it out explicitly as this expected value, and then if you expand this, it's like, depending on if it's regression or classification, there might be integrals, there might be sums. But nonetheless, all of them are going to be with respect to some PMF or PDF of like y given x times p of x, something like this. So you're really going to need to know the distribution. And so the issue is like, right, that this guy at the end of the day is not known. And I'm really just replaying the same story over and over again, but hopefully this will, I really just want to point out that there was a choice we made now, because now we said we have data from this distribution that was IID, and we're still going to keep that whole assumption. And then we said, what should we do with that data? What should we estimate with that data? Or like, what can we use it to understand more about? And we said, this is an expected value. We can construct samples of this. We can, like, based on our XY samples, we can construct samples of this loss, and we can just take like its sample mean and say, okay, we can get an estimate of the risk. And we called that estimate the sample mean estimate or the empirical risk or the estimate of the expected loss, whatever you want to call it, and we just estimated this random variable directly. Or sorry, this expected value directly. Okay, that was one choice of how to do this. An alternative was, well, I mean, we talked about it roughly before, but the alternative was like, if we want this thing, if this is what's causing us the issue of computing this, why don't we estimate this distribution instead and then just calculate the expected value explicitly using an estimate of this and then be done. Okay. And so that's going to be the idea, like estimate this. And we're gonna do, okay, so that's what we're gonna do, and then we're just gonna compute this expected value. But it turns out that we can even save a little bit of a struggle to do this by making another observation, which is like, if we knew this thing, well, we can compute what f base is. Like, this is just a set of calculations, which we're not going to go through, but you can expand this out and then, you know, you have to pick a loss. So we're going to pick a loss. Okay, and this is going to be important for this calculation. So we're going to assume now that we have the squared loss and we're in the regression setting. And we're going to redo this type of story for the classification setting. And this is actually how we're going to end up doing classification from this procedure instead. Okay, so we kind of want to get an estimate of this distribution so we can then calculate an estimate of this expected value with an estimate of this. Okay, so we pick a particular squared loss and we pick the regression setting. So now we know our labels are like in R, like the real numbers. Let's say we have the squared loss. And before doing any of this estimation stuff, we can just explicitly calculate what f base would have been. It turns out that you can just do this calculation. And of course, it's going to still depend on this. But the point is, it's going to be quite a bit simplified from this expression. And if you do that calculation, which is not hard to do, I mean, before we even do it, let's visually kind of guess at what this might be. So we've seen kind of an idea of f base before. So how did we kind of understand what f base is? One way to understand it is, well, we somehow need to get an understanding of this distribution. And one way to view what the distribution is just to plot a bunch of points from it, like an insane amount of points. And we had something like this, like you just plot in a lot of them, and maybe if they're more dense around this area, then it's more likely to be around there. And yeah. And so, of course, this is just like a rough approximation of what the distribution kind of looks like, but it gives us an idea of how many points you can see where. Okay. And then f base would have been like the thing that minimized that risk. Okay. And really, in your assignment stuff, to kind of get this visualization, you want to take the number of data points to kind of as many as possible to get an idea of the density at each of these regions, which somehow gives you the density of that distribution. Okay. And now I want to take a guess at what f base might be for some arbitrary distribution, right? If I change the distribution, then I might get different data points. But in general, what would you like think that f base would be? And f base is a function from x. This is x to y. Okay. And this is whatever. The y-axis is some number, the thing you're trying to estimate. And notice that f base has to output a single number for every x. So that means, I mean, f over here, you'd have to estimate, and you can see that from this curve, right? F base is just a single number. It can't output a bunch of data points. It outputs a single number for each x. Question is, what should you pick for this value at each one of these x's? And it turns out that a good choice is to pick the expected value of y conditioned on that value of x. And that is actually the solution to the argument above. So the best choice, or the f base, is actually for this regression setting with the squared loss, is going to be always equal to the expected value of y given x. And here I will have to actually plug in a value of x. So f base for a particular x vector is equal to the expected value of x conditioned on the random variable x equaling little x. And that should kind of make complete sense. It's like if I had to pick one number for any value of x, I should just pick the expected value, it turns out. Okay. And why I'm writing this is because now you can expand this expected value, right? And we know how to write an expected value. It's either going to be an integral or a sum. But since y is continuous in this regression setting, it's going to be the integral over your set y of labels of the random variable y, well, I guess it's instance little y, times now the corresponding PDF of y given x equal to little x, right? Yeah. Okay. So the reason I spent all this time is because this step is kind of very important to understand what we just did, which is we now, like we can, it turns out that f Bayes has this like closed form kind of solution. It turns out it's always going to be this expected value of y given x for this regression setting with the squared loss. And one way to, design a learner is to just kind of estimate this quantity directly, right? So the argmin business has already been done over the true risk. Turns out to look like this. And now all that's left is to just do this calculation. And to do that calculation, all we really need is this quantity. And so we just need to estimate that PDF. Okay. So does that make sense? Like all we need is just some procedure to estimate the PDF, which is what we're going to spend the next 2 lectures on. Two different ways of doing this. And if you estimate it, all we're going to do is just plug in the estimate, which will not be exactly this, but we'll plug in an estimate of this, and then evaluate the integral. And we will see that the integral is very easy to evaluate for the estimate for certain reasons. And that will be our estimate of f Bayes, because it will be using an estimate here. And then we'll compare to how that predictor looks relative to like the closed form solution, for instance, let's say, that we've used before when we had a linear function class. And we'll see how the linear function class maps to certain choices here and so on. Okay. Great. So let's spend the rest of the time to use the data set. So yeah, this is the idea. Let's use the data set to estimate P of y given x. Okay. And this is where maximum likelihood comes in. So maximum likelihood estimation is a procedure to estimate, roughly speaking, like to estimate, let's say, PDFs or PMFs using data. Well, and so we're going to first study, as we've done with optimization before and probability and so on, we're just going to take a step back from all this machine learning business for like maybe 40 minutes, or maybe the whole rest of today. We'll see. And then it should be obvious how we're going to just apply this to our setting, because we just changed like the random variables and everything is the same. Okay, so how does this work? That's not how you spell basics. MLE basics. That's what we're going to look at. Oh, and another note I wanted to make is if any of you are reading like the course notes PDF version online that's written up, not by hand, not like the iPad notes, and you have the version before yesterday night, you might want to download the updated version that I changed last night, because after reading that section, I found out that I don't know what I was doing last year, but there was a whole lot of mistakes in there. They're not terrible mistakes. It's just like terminology was kind of funky. So yeah, it's a good idea to just download the updated thing if you read those. Okay, that's just a note on that. And let's get into it. So this is how it works, this maximum likelihood estimation basics. So the assumption in maximum likelihood is that there is a data set. But think of this data set nothing to do with machine learning from now on, just a data set that is just a joint random variable of n random variables. We'll call these Z1 up to Zn. And it's an element of some outcome space. So each one of these random variables is in Z, and then you have n of them. Okay, and Cartesian products. And this random variable has a corresponding distribution P of D, and then a PMF or PDF P of D. Okay. And the assumption that we'll be having, this turns out to, you can already see it. Okay, let me say it this way. So assumption is these ZIs are IID with the same distribution. And that distribution, right, we need a distribution for each one of these. And so that'll be like P of Z. That's its distribution. And PMF or PDF, little p of Z. Okay. Notice already how this is very related to our setting, and it should be understood in the other direction, which is this maximum likelihood stuff was well studied, and then the obvious, if you're trying to do things in machine learning and so on, or whatever, you then, pick a setting that's already been well studied, that we already know how to do things. So it should be thought of like, the IID assumption, I don't know, 8 lectures back, I said that we're going to use this mainly for like, convenience because of the way the algorithms and stuff we can design. And it goes like the other way, right? Which is like, if you know about this, then that's why we chose the assumption. It's not like we chose the assumption, then it's like, oh, wow, all this stuff is very useful now. It goes the other way. It's like we knew there was a lot of useful things if things are IID. So that's why we made the assumption to begin with. Okay, so hopefully it makes sense when you look back. And the study is something like this. So like if we actually maybe let's not say this first. Okay, so since things are IID, we can just write out something that we know, which is a property of something being IID. So okay, let's do this. Let this calligraphic D equal to little zi z1 till zn be a fixed data set. So this is like you've sampled some data set. You already got your data set. Okay. And then if you look at the corresponding PDF or PMF of this data set, it looks like this. It's the joint PMF or PDF. And I just want to remind you, this is the property we're going to use, is that since things are independent, the first thing we get is that this can be written as the product of these P of Z, PDF or PMF. So we've already seen this before, but it can be written like this. I'll just write it explicitly. This is P of Z, Z2, all the way up to, maybe I write a big circle, dot, 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 big circle for multiply P of Z, Zn. Okay, so this was independence. And at this point, hopefully you've seen this a few times and seen the use of it. And the second process we're gonna, or the observation we're gonna use, just to make this very explicit, this technically has some PDF for Z1 and for Z2 and Zn. But since they're identically distributed, right, you can replace all of these with P of Z. That's the identically distributed part. So we're going to make this very explicit in 2 steps. That identically distributed allows you to change from these are technically different PDFs, but then since they're identically distributed, you can change them to the same one. Okay, we've seen this before. And now, just to save some space, we've seen the summation notation. I probably should have in the math review mentioned that there's an equivalent for products, multiplication. And instead of having a sum symbol, there's a big pi for product. And the story is the same. You write I equal to 1 till n of P of Z of little zi. Anyway, that's just to save a bunch of space, that these things are just multiplied together. Okay, great. So all we've done is just rewritten that this PDF is the same as this thing, if things are identically IID. But the observation now is that if I would like to get an estimate of this, okay, and if I would like to somehow understand what's the distribution that's generating my data, it'll be just sufficient to estimate this, because if I estimate this, then I can take its product n times, and that's the same thing. Okay, so we're really going to ask how to like estimate this quantity. And then kind of the natural way, well, like one way you would want to do this is like you have data points. You don't know what this is. So you can just, I don't know, try a bunch of different P's. Like plug them in, plug in your ZIs for all of your data points, calculate that number. And like probably if the number is higher, then that means that was more likely that that was the actual P that generated your data. And if the number is really, really tiny, it's probably unlikely. And that's exactly what MLE is going to do. So we're going to want to pick the, okay, so we don't know what P of Z is. And so we're going to want to pick a P. We're going to want to pick some P that makes this quantity as big as possible, right? Makes the probability as big as possible of seeing the data. And so this is the argmax P. We'll just keep it as P. And just argmax P coming from, okay, it's going to come from some set. And here, similar to before, we're going to have to pick some set of like PDFs or PMFs that we're thinking of, we think it might be coming from. This could be all possible PMFs or PDFs. But you're going to imagine that we're going to need to restrict this to some function class soon. So I'm going to call that H. This is the set of like PMFs or PDFs you're going to consider. And yeah, so the choice of this argmax is going to be kind of the one that makes what is called the, okay, so the P, okay, so we're going to pick a P here. This P, the result of this is what we will call like the P that is most likely, or the most likely P given this type of data, okay? And so this is going to be, oh, I've given a name, it's going to be P MLE. And MLE stands for maximum likelihood estimate of the corresponding distribution that generated our data. Okay. And this quantity can be thought of as like, we'll see it later, this is called like, okay, not this. This is called like the likelihood. Wow, how do you spell likelihood? Likelihood, okay. The likelihood of P given the data. And for different P's, this will be a different number, okay? And so that number is to be interpreted as the likelihood. It's just a number that quantifies, you know, the likelihood of P, because it's, I mean, it's just a number. And that number is called like the likelihood of the corresponding P. Different P's have different likelihood values. And we're going to want to pick the most likely P. In the sense, it's the P that has the largest value for this. Okay. Now let's do like kind of understand this with an example. And hopefully it'll become even more obvious that this makes sense. So let's do it with our favorite example of flipping a coin. And so these ZIs are coin flips. And so coin flips have some probability of being heads, 1 minus that being the probability of tails. That's called a Bernoulli random variable, as we've seen. And the probability of heads is, we're going to use that parameter alpha for that. And we're going to call it alpha star, because this is the true probability, or the true parameter, the true probability of being heads. And you can already imagine that when we're going to try to, you know, pick different P's, we're really going to be searching over different parameters. And you can already see how the whole story of like, we're not actually searching over functions, right? We're searching over parameters that have one-to-one maps to our functions. And okay, I'm just foreshadowing how everything we've kind of seen is going to be very useful now. Okay, so coin flips. Probability of heads, alpha star. This is like the ith coin flip. And we assume that each one of these are, sometimes it's written here, it's like these are all IID. Okay. And what does that mean? Well, that means that the corresponding PMF, because we know this is a discrete random variable, right? The corresponding PMF is equal to, and there is a nice, like, you could write that, it's equal to 1 with probability this, and otherwise it's equal to 0 with probability that. There turns out to be like one mathematical closed form expression that we've written maybe a long time ago, but it looks like this, which is it's alpha star to the power of the value of z. And remember, zi's, they all come from either, they come from the set that gives you a value of 0 or 1. 0 for tails, 1 for heads. And then it's 1 minus alpha star, 1 minus z. Okay, this might look very weird, but turns out very easy to understand. So let's just do the two cases. What happens when z equals 1? I want the probability to be alpha star. So let's just plug in z equals 1. Z equals 1, well, you just get alpha star here. Z equals 1 here, you get 1 minus 1, you get 0. Anything to the power of 0 gives you 1, so you end up with alpha star, right? So the probability of 1, which is what the PMF tells you, is just alpha star. And if z is equal to 0, you get 0 here, this becomes 1. You get 1 minus 0, so you just get 1 minus alpha star in the other case. So hopefully you agree this is the correct expression. And we will occasionally label this. Okay, we'll do this labeling a little bit later. So, okay. So now what is the obvious, like if we know that we have a coin and we know that there's only two possible outcomes, the obvious P that we should search for if we don't know alpha star, okay? So remember the settings now, this is the underlying process that's generating our data, but we don't know the distribution. We don't know alpha star. We'd like to estimate the distribution. Since we know it's Bernoulli, the natural thing is we really want to just estimate alpha star. And so this class of distributions, or sorry, class of PMFs that we're searching over will be as follows, right? It's just going to be all of the functions, right? All of the PMFs, such that first of all, they have, the form of a PMF. So they map from the outcome space to 0, 1 closed interval, right? These are the probabilities. And they have a special form, and that's because we know what kind of random variable we're dealing with. And that special form is that P of z for any z is of the form alpha to the z, 1 minus alpha to the 1 minus z. Okay. And yeah. And alpha is just some parameter that's 0 between 0 and 1. So that's our, what you would call like a, I guess, PMF function class or PMF class or whatever. Sometimes people call this the hypothesis class. That's why we use H. Okay. And so the point of the story is that any P in here has this form. And so it can be identified by an alpha. And so from now on, when I write that, like, when I write P as an element of H, I'm actually going to just subscript it by alpha. And that's going to be the corresponding alpha it's based on. And that's because every single P in H can be written as this like P alpha, where, yeah, we know what it is. It's this thing. So we've seen this a bunch, which is that every single function in this class has a one-to-one correspondence with some parameter. Okay. And so the above, the true PMF can now be written using this notation as P of alpha star of z. Okay. Where this is coming from the function class. Great. And so now we want an estimate of P of alpha star. And we're going to use the corresponding maximum likelihood calculation above. So let's just take it here. And so that's going to be what we want. And okay. And so we search over this function class H. But now you can imagine that similar to before, in this whole empirical risk minimization where we choose a function class to be like lines, and those are based on parameters, we're not going to be actually searching over this function class. We're going to be searching over, the parameters. And so we replace this. Well, first of all, we should replace this P over here with the corresponding, what does P look like, right? So we're going to be actually taking this and plugging it in here. So maybe, yeah. So erase this. We know P in this function class always looks like this, right? And so instead of searching over P's, we're going to be searching over alphas. And alphas are in this set 0 to 1. Okay, so that's looking really nice now. This is like something we kind of know how to do things with now. Okay, this is in the set 0, 1, but that's okay because we're not going to actually deal with this in our setting because our parameters will be in the real numbers for now, later on. And so yeah, we just have like an optimization problem that we really need to solve. And this is like your g of, you should think of this as like your g of now z function. Before we always called this like, we labeled it purple before. And hopefully if this is convex, which it will end up being, you can just use all of your strategies for before, for minimization, and then you just take its negative, and then you can do maximization as we've heard, and we'll do that. And this quantity will not be P MLE, of course. This will be alpha, the maximum likelihood parameter. And so now P MLE will actually just be equal to P alpha MLE, right? So that's how things work now. It's the corresponding PMF we output is actually just the PMF based on the alpha that maximizes this quantity. Hopefully that whole mapping makes sense. We've already had a lot of practice with that. And the hope of all this, right, is that this is close to P of alpha star, because hopefully alpha MLE is close to alpha star, which would give us the corresponding P of Z. So hopefully this process makes sense now. This PMLE is hopefully approximately equal to P of Z through this process. And this is like an exact example. Okay. And I want to mention one more thing about notation. So now we've already said that this is like the likelihood, right? And so this is called like the likelihood function. And this is like the likelihood of parameter alpha given the data. Okay. And now maybe let's do a plot of how you should think about this as well for this flipping coin case. Okay, so for flipping a coin, you can only get two values, which is 0 or 1, tails or heads. Right? And let's do an example where we gather a data set and just see what would the alpha that we pick end up being. So let's say the data set is 5 points. Right? Okay. And so this time I'm going to draw the data points. I'm just going to draw x's on the 0 or 1, and I'm going to draw 5 of them. So maybe your first one is here. So you get a tails. Then maybe you get another tails. Then you get a heads. Then you get another tails. Then you get a heads. That's a particular data set. And it was generated by some distribution. I don't know what it was. We don't know what it is, but this is what we got. And the question is, what should be like the PMF be that, like, what should our guess be of that PMF? And so we need to guess that PMF, right? And like guessing that PMF really just means I need to guess the probability of heads, because the probability of tails will be 1 minus that. And so looking at this, like the first obvious thing is that like I probably should pick heads to be less likely than tails, right? So alpha, if let's say this is 1 and this is 0.5, I probably should guess that alpha is less than 0.5 because I only got 2 heads. Like that's just like, or so far we're just building like intuitive logic, and we'll see what we actually get when we do the calculation above. And so maybe alpha is somewhere here. And then 1 minus alpha is going to be above. And so, yeah, I don't know. Maybe a reasonable guess is that alpha, this is the probability of heads. The probability of tails is this. Okay. So hopefully, like, it makes complete sense that alpha is at least going to be below 0.5. But the question is, like, what's the best one? Should I pick 1 for alpha? Should I pick that? And okay, without doing the MLE calculation above, maybe a reasonable thing, if you want the probability of getting heads, is just take the ratio of heads to total number of flips, right? So maybe alpha should be equal to 2 heads over my 5 flips, right? So 0.4. And okay, that's just like an intuitive feeling of what that might be. And it turns out that indeed, this is exactly what alpha MLE will evaluate to. And I think this might be on your assignment to do this calculation or something like this. I don't know. Or maybe it's an example in the notes. But so hopefully that checks out that this makes complete sense of what's going to happen. It's going to turn out that the alpha, like, right, if you do this optimization, that the alpha that makes this quantity the largest will be 2 over 5. And that should make some intuitive sense. Okay, so this indeed will actually be alpha MLE. Okay, great. Let's do another example, which is the one that's actually going to map to our setting of a regression, and we're going to make use of. This one will map much more to the classification setting later on, because you can imagine you either label 1 or 0, let's say in binary classification. Okay. Are there any questions about that? Okay, so now let's do a case where the random variable is continuous and not a coin flip. We're going to do Zi, continuous random variable. We're going to pick our favorite distribution, or it seems to be the favorite distribution of statisticians, and we can talk about why, but that's going to be the normal distribution. Okay. And notice something, that all these distributions that we kind of talk about, they're all what are called parametrized by some parameters. They're all based on some parameters. Or said in other words, they are themselves functions. But they're functions that you only need a few numbers, a few parameters to fully describe. And you can see how this is a really nice, I mean, same story when we had the polynomials, where every polynomial up to some degree can be described by its coefficients. Same story with all of these, like what are called parametric distributions. And so MLE really is a process to do this kind of thing when you have these parametric distributions. It's going to be a method to find the parameters when the distribution has some parameters described by it. And notice this beautiful mapping that when you have parameters describing some function, minimizing or optimizing is just searching over those parameters, which we know how to do. Okay, so distribution has 2 parameters, mu star and sigma squared. It is sigma squared, or do we call it sigma? I think it's sigma squared. Okay, this is the variance. And technically there should be like sigma star squared, right? And we would need to learn kind of both of these parameters, and we need to optimize. But turns out we're not going to waste our time with this. You could do this, and you'd have to solve 2 problems. Well, you'd have to solve the problem together for both of them. But we're just going to simplify things, and I mean, at least for this example, we're just going to say that it's 1. Just for some reason, data was always generated by a distribution that had a variance of 1. It's a weird assumption, maybe, but that's what we're going to do. And now we're just going to study how to estimate mu star. Okay. So that's what's going on. And maybe you can think of this as like a, we had a coin before. Maybe you could think of this as like, this is, let's say, the height. It turns out the height of people seems to be normally distributed. So this is the height of the ith person. And yeah, this will be kind of the rolling example we go with for the continuous case, height of people. And all that tells us that this normal distribution thing tells us that the PDF is the PDF of a normal distribution. PDF of a normal distribution is the following. When you have sigma squared, the variance equal to 1, it's just 1 over 2 square root of 2 pi times the exponential function, right? Okay, I'll write this, but this just means exp just means e raised to the exponent. And since the exponent is big, we write it like this, which is, I think we've done this before. And the exponent is, okay, well, what's the exponent? It's your value that you care about, the density kind of at that value, relative to the mean, right? This is the expected value, the mean of the distribution, squared, it's the squared distance, and then it's divided by the variance, 2 times the variance. And since the variance is 1, it's just 2 here, right? And this, yeah, there's 6, like, just a side note, like, exponential to like the power to a is the same as e to the a. These are equal. Great. I feel like we should know this by now, but just in case. Okay, and now what is our function class of things we should search over? Well, in some sense, this is our assumption that the data came from this. If it really did come from it, then what we should do is we should search over normal distributions with variance 1, and we need to find this mean. We don't know this mean. So that means our function class is going to be, we'll take this definition and we're going to just change the kind of constraint or property that it needs to satisfy, which is now as p is a map from the outcome space, and since it's a PDF, this is not going to be 0 to 1. This is going to be 0 to infinity, right? The density could be infinite, well, as up to infinity, and the P has a certain structure, and the structure is the following, right? It looks like this. So make that much smaller. And P equals this. So maybe I'll put it down here. And P of Z equals the following. And the parameter mu, the mean, is an element of the real numbers. And that's H. Okay, the same procedure goes. So let me just copy and paste this stuff. Now the procedure is going to look like this. And we'll actually solve this now. We'll actually do the maximization, because this is going to be actually the assumption we're going to end up using for the machine learning setting. So that's why we're going to work this out and then just change a few things. Okay, so we want to get PMLE. PMLE is not alpha MLE. It's going to be the mu MLE, which I will define in a second. This P of Z up here, well, this is equal to, in other words, make this a bit smaller. It's going to be equal to P of mu star, using our notation where P of mu star comes from here. And yeah, so story stays the same. The only difference is this argmax and stuff is different now. What's different? First, we are getting the mean estimate, mu MLE. We're taking an argmax over mean estimates or expected value. Parameter is mu. Mu is no longer in the 0-1 interval, it's in the reals. Very nice. We know how to optimize over, the real line. This is one-dimensional optimization, which is even better. And all you need to do is change this thing now, right? And so let's do that. Let's change that to the above expression. Okay, so it's no longer this because we're not using the PMF of a Bernoulli. We're just going to change our PMF because we're searching over a different PMF now. And that's because we assumed, or the data really was told to us, or the data really did come from this normal distribution. So that's what we have. And of course, it's not mu star here, but just mu, because we're trying to search over the corresponding mu that makes the product of this expression for our data points. So you put Zi here, and I probably missed that above. Here, this is, of course, Zi, right? That's what this product is over. It's over the values of this for your data points. And yeah, and this will be our new likelihood. And this is like the G of Z's we've been trying to optimize in the past. Great. And so we're going to solve this now. And before we do that, let's have the visual kind of story of what is happening. What is mu MLE doing? What would it pick? And to do that, we should just plot some data like we did with the coin flip and see how to interpret this. And this maybe has a nicer interpretation in some way. I don't know about nicer. Well, it has some interpretation. Okay, what's our x-axis? Our x-axis is going to be data point, like the random variable z, and now we're going to have a bunch of different data points. I don't know, maybe n is like, I don't know, let's just put a certain number of them. So here's maybe your first sample's here, and then another one's here, and another one's here, and another one's here, and then one you get out here, and then here's another one, and this, and maybe another one over here. Okay, how many points are there? 1, 2, 3, 4, 5, 6, 7, 8, 9. So data set of size 9. We plot these 9 points. And now we'd like to pick the normal distribution, well, really the PDF of this normal distribution that, maximizes this quantity. And this is to be once again read as, this is the likelihood, it's a number that describes kind of the likelihood of getting of the underlying sampling distribution's PDF being this. Okay, so it's the likelihood of mu given this particular data set. And so which mu would have the largest likelihood? Well, it's going to turn out actually that you can usually, one way to think about this is you plot like a normal distribution. So we've chosen the variance to be 1, first of all. So we can plot some normal distribution. Let's say this is a normal distribution with variance 1. And the only thing we're changing is its corresponding mean. So you can think about this as all we're doing is we're just literally going from left to right, from like negative infinity to positive infinity, sweeping mu. And I don't know, let's look at one case. So suppose we had, this has a certain mu, this normal distribution. And what you would do is for this mu, you would compute this quantity, right? And what does that quantity, what is that quantity? That quantity is just like the PDF at this value times the PDF at this value times the PDF at this, and this, and this. All of them multiplied together. And in other words, kind of like the, well, we saw it's actually very much like the probability kind of getting that data under that corresponding PDF. Okay, and so you do this procedure, and you can see that clearly if we did this whole sweeping business, and let me delete some of this dotted line stuff, when you're over here, this product would be tiny, tiny. And that's because you're multiplying a bunch of points that are really close to 0 in value. And if you sweep this and go all the way to here, you also have a tiny, tiny thing because it would be like all these points are also close to 0. Multiplied together, you get something like 0. And so what you really want is you want to move this somewhere where most of the points are living. And this is like almost exactly what you would expect the best choice of parameter to be. And so this value over here will give you mu MLE. Okay, that's the visual story. Yeah. Can we, yeah, how about we, just for fun, have a guess at what the mu MLE is going to be before solving this problem, like the actual closed form expression of it. Because I'm going to give it away, which is that it's almost obvious what you would expect it to be. Is there anyone that wants to guess what this might be? Yeah. Sorry?
The average of the
Sorry, the average, oh, yeah. Okay, that's right. So it's just going to be the sample mean of the 9 data points, which would be, if you take I equal 1 to n of these zi's, you sum them up, so that's their values, right? You sum up all these values, and you just divide by the number of data points. And now we're going to spend like more than a page doing this calculation just to find out that it's the sample mean, which we've done in the past, I think, for similar things. But you can imagine when things are more complicated, it might not be the sample mean. So for the variance, you don't actually get this expression, or I can't remember. Actually, I think you do get like the sample version of it, but it's not the usual sample variance. You don't have like the 1 over n minus 1 thing. You just have 1 over n, if I recall correctly. So that's interesting. Okay, so let's work out that calculation for the rest of the class. And next class, we'll just literally follow the exact same procedure for the machine learning supervised learning setting, except now we're going to assume that the corresponding yi's, the labels, given a particular feature, follow this normal distribution. And that is to be interpreted as follows, just to give you like an idea of why we care about, is for a particular x, we're going to think of it as having a normal distribution like this. And then we're going to calculate the corresponding kind of maximum likelihood estimate of the corresponding conditional PDF, right? Which is what we wanted. That's this thing here. And so we're going to assume, and this is a bad plot, we're going to assume that each one of these kind of data points for a fixed x was generated from a normal distribution. Okay, so we'll come back to that. Let's work this out. It's not too hard. Okay, so all we need to do is solve this problem here. Yeah, so this is our expression. And maybe I just want to write one thing before as for notational sake. So we start with mu MLE because this is kind of like the general procedure you would take. So you want mu MLE, like you write MLE in the subscript of the parameter you're interested in. And now this is your kind of, what is a boilerplate, the boilerplate math that you just repeat every single time for this MLE calculations, which you will do quite a few of. So you want to minimize, you want to get the argmax mu from whatever the domain of your parameter is, of the product of n I equal 1 of, okay, so now here is a notational thing. So here you would write p of mu of zi, right? And all we did here was we just plugged that in. Like, oh, sorry, this thing was exactly that. It was just plugged in. So that's what we're going to have soon. But before plugging it in, people seem to, I don't know, abuse notation is the right, I guess, way to say it. And instead of writing mu in the subscript, mu is just your parameter. They'll actually remove it from the subscript and say that, oh, it's like kind of like saying that, this is conditioned on mu, which is absolutely not what's really happening here. But these turn out to be the same. So this is what people do. And this is exactly the same as p of mu of zi. And this is what you'll see often. If you ever read MLE things, this is how it will look. And so, yeah. And so you're changing the mu, which changes the corresponding p. The same as this. Okay. All right. So, yeah. We would naturally just plug this in and continue trying to solve, but let's try to make things map a little bit closer to things we're familiar with solving. So two things that are unideal here. We have a max, and we would like it to be a min because, we've always minimized. That's going to be easy to solve. We'll just change it to the negative. But the thing that's a little bit worse is that the only way we know how to minimize is, how are we going to minimize? We're going to take the derivative and set it to 0, or we're going to do gradient descent. But for both of these, we need to take a derivative. And if you recall anything from calculus, taking derivatives of the product of a bunch of things is kind of horrendous. And so it'd be really nice if this was not a product. And the trick for this is to, okay, so we want the argument that maximizes this expression here, right? So what you're going to want is you're going to want to okay, so there's this property. Let's just draw things. How much time do we have? Okay, let's draw things. Okay, let's just draw things like this. If you have like a parabola and you find its minimum, fine. It turns out, okay, and the argmin would be this point here, right? Well, this would be the actual argmin, the corresponding value here, the value on the x-axis, or here it's the mu axis. It turns out that if you take this function and apply on top of it, so it's called compose, or apply a function on top of this, that's what's called monotonic, which means it's monotonically increasing, or I guess decreasing would be fine. So take a function like this. Let's draw it like this. And you apply it on it, then the minimizer still stays the same. And that's because the function just gets kind of skewed. It ends up being I don't know, it becomes something like that. That's our new function. If you take the blue function and you apply the black one is, okay, this is not a good example. The log function would look like this. Then it might become something like, I don't know. Okay, so that's how our blue would be transformed if we apply this black one on top of it. We're going to do this in a second. This is like the log function. And you still end up with a function where the minimum is going to be at this, or the minimizer, the argmin is going to be at the same value. And you can do this by plotting a bunch of things on Desmos and stuff, but we're just going to kind of take this for granted. And so the first thing you're going to want to do is apply some function that's going to help with this product. And it turns out the logarithm is extremely helpful. Okay, so in other words, I would like to apply a function that causes this product to disappear and does not change the minimizer, or the argument, not the minimizer, the argument. And that function turns out to be the log. So I'm going to apply the log to the entire thing. And the argmax will stay the same. The max might change. It likely will. But this stays the same. And this is what is called, because of things are monotone. I guess I'll write it. Because the log is monotone. Okay, how much time do I have? Not very much. Okay, let's just do couple more steps and we're almost there. So next thing is, there's a property of the logarithm, which you might remember, which is like log of a times b is equal to the log of a plus the log of b. And so this is why we applied the log function, because the product becomes the sum of things. And so in other words, all that means is you can remove the brackets. You can take this product. Well, actually, you can just completely remove it. And we're going to change it to a sum of logs. Right, so that's all this said. It said sum I equal to 1 to n of these log terms. Beautiful. And then the last step is that we don't want to maximize, we want to minimize. And we've learned before that if you take the negative of the function, then its argmin is equal to its argmax. So you can take the argmin of the negative of this function. Okay. And we'll pick up from here, but the one thing to say is this quantity here has a special name. This is the first quantity here. It's called the log likelihood for obvious reasons. So this is the log likelihood. And this whole thing together gets the name negative log likelihood. And this is usually what you minimize. And the only reason we did this is because we're so used to minimizing things. And that's well known in the literature, so people just always try to get the minimums. So you could totally just maximize in the same way. Okay. And then next time we're just going to solve this argmin, which is a couple more lines of just taking a derivative and setting it to 0. Okay, so we'll continue on Thursday. Thank you. Oh, I guess on Tuesday. It's Thursday already. So have a good weekend, everyone.